Hi, in this video we're going to be talking about logarithms. This is another topic that sometimes students need refreshing on. You cover this in high school, but if you don't use it a lot, you forget some of the rules or why we even use logs in the first place. So that's the first question that I want to answer. I remember being a student and you get introduced to these things, but seldom do we have justifications for them. So just like scientific notation is merely a useful way of communicating, logarithms are another useful mathematical operation. That's really all they are. There's nothing special about them per se. It just helps us communicate big and small numbers, and I hope to show you that in this video. And in the process, also remind you of a couple rules related to logs and how to work with them mathematically. So the first thing that I want to remind ourselves of simply is the log of 1. And if you have a calculator handy, I would encourage you to take it out and put in the number 1 and take the log of the number 1. And what you will see is that is 0. So that's a useful thing to remember, that there's an identity here that the logarithm of 1 is 0. Now, the first question that we might even say here is, well, what does that mean? What does log mean? And I don't know why log got selected. There's a history here that I don't honestly know. But all this really is a mathematical operation. Just like addition, subtraction, multiplication, division that we're familiar with, we accept, we don't ask why do we add two numbers together, really. We don't ask why do we subtract two numbers. We know that those are useful things to do. Well, similarly, taking the logarithm of a number is useful. And honestly, the only real use that I see for it is to make really big numbers a lot more manageable and really small numbers a lot more manageable. And we'll see that. So if it helps to demystify it at all, just think that it's nothing all that special. It's just yet another mathematical operation, one that we use less frequently in our daily life than addition, subtraction, multiplication, and division, but nonetheless just a mathematical operation. So the log of 1 is 0. You might even know what the log of 10 is. Well, the log of 10 is 1. Now, if you don't know that, that's perfectly fine. Take your calculator out, make it do the logarithm of 10. However you enter that into your calculator, just prove that to yourself. And then for the rest of your life, you will probably never need to type that in again. The log of 100, go ahead and do that on your calculator. And I'll pause and withhold the answer for a moment. Well, the log of 100 is 2, is what you should get on your calculator. Log of 1,000, go ahead and do that. Now, I talked earlier in a video about pattern recognition. You should see a pattern emerging here so that when I write the log of 10,000, you probably don't even need to put this into your calculator if you've been paying attention to what's happening. This is going to equal 4, and you guessed it, the log of 100,000 is 5, and the log of 1 million is 6. Now, notice what's happening here. The number inside the log is going up by a factor of 10, which we also call an order of magnitude. So when we go up by a factor of 10 or up by an order of magnitude, the log of that is only going up by 1. So when we go from 1 to 10, we've multiplied by 10. We go up 1 log unit. We've multiplied 10 by 10 to get 100. We've multiplied 100 by 10 to get 1,000. And in each case, we've gone up by 1 log unit, all the way up to 10 to the 6th. Now, in a previous video, we looked at scientific notation. We saw that we could write a million in a more simple form, and we could write a million as 10 to the 6th. So we can also say log of 10 to the 6th is equal to 6. How can we rewrite log of 100,000? That would be log of 10 to the 5th. And we said that that is equal to 5. And log of 10 to the 4th is 4. 1,000 is 10 to the 3rd. And we saw that that's equal to 3. 100 is just 10 times 10, or 10 squared, and that was 2. And we can then just think of this as the log of 10 is equal to 1. And we could even think of this as, or 10 to the 1st if you want. And we could think of 10 to the 0 power would be 1. Anything raised to the 0 is 1. And that turned out to be 0. So you see that whatever was in the exponent here in our 10 comes down. So we're dealing with what's called the base 10 log here, which is a common base that we operate in chemistry. And you might even remember the rule that if you have something like log of x to the 4th, the 4th comes out of the log term, and you can rewrite this as 4 log x. And again, if you don't remember these things, but they're kind of vaguely familiar, just plug in any old number. So let's do log of 3 to the 4th. Okay. If we take 3 raised to the 4th power, I'd encourage you to do this on your calculator. You would get log to the 81. And if we take the logarithm of 81, we get 1.908. Now, we could also follow this operation, which said this is going to be 4 times the log of 3. So if we calculate the log of 3, so go ahead and do that on your calculator, we end up with 4 times 0.477. So we take 0.477, multiply by 4, and sure enough, we get 1.908. So in thinking about our logarithms here, we've already arrived at one of the useful manipulations of logarithms, that if we have the log of a number raised to an exponent, that's also equal to that exponent times the log of whatever number that was. Okay. So I want to come back to this, though, as this is the thing that actually makes why we use logarithms. And you notice what happened here. A million, the number 1 million, which is a big number. If you write a million, it takes up 7 spaces of typing. When we take the logarithm of it, it simply reduces to 6. So we take this really big number, right? So I'm trying to illustrate with my hands this really big number, and we're shrinking it down to 6. Right? So the whole scale from 1 to a million. Think about if you were to write those numbers down, 1, 2, 3, 4, 5, 6, you'd have this very long string of numbers. On a logarithm scale, that whole string gets compressed to 0 to 6. So we take a 0 to a million and squish it into 0 to 6. And all that really helps us do is deal with big numbers. And sometimes in science, we have to deal with big numbers, and we find that logarithmic operations with big numbers are helpful. Similarly, we sometimes deal with small numbers. So let's look at what happens if we do decimals. So go ahead and in your calculator, do the logarithm of 0.1 and do the logarithm of 0.01 and the log of 0.001 and log 0.0001. And start looking for a pattern to emerge. So in this case, we have something where we've gone 1, 2, 3, 4, 5, 6 decimal places over. We could rewrite this as log of 10 to the minus 6. Well, we just saw the rule that if we have log of something to some other number, that comes out, and we get y, we'd get y times the log of that number. So this would become minus 6 times the log of 10. But what do we know the log of 10 to be? It was the very first thing we calculated, or the second thing we calculated. The log of 10 is just 1. So the log of 10 to the minus 6 is equal to minus 6. The log of 10 to the minus 5 is equal to minus 5. The log of 10 to the minus 4 is minus 4. So notice a lot of what we've done in previous videos is coming together. We talked about scientific notation. So here our scientific notation is helping us out to simplify these problems. If you just write it like this, you're not going to recognize that the answer is -5 right away. So by using the scientific notation, we're helping ourselves become faster problem solvers. This would be log of 10 to the minus 3, which is equal to minus 3. Log of 0.01 would be log of 10 to the minus 2, or minus 2. This is log of 10 to the minus 1, or -1, and then we'd be back to the log of 0. I'm sorry, the log of 1, which would be 0. So here again, we see we take these really small numbers. 10 to the minus 6 would be what prefix? Hopefully you said micro. Milli is 10 to the minus 3. Micro is 10 to the minus 6. Nano would be 10 to the minus 9. So if we had log of 10 to the minus 9, that would be minus 9 as the logarithm. But notice 10 to the minus 9, 0.000000001, that's a very, 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 very teeny number. And we're representing it now when we take the logarithm of it as minus 9. So just like here, where we took really big numbers, each one 10 times bigger than the next, but only adding one log unit. When we have decimals, each one of these is 10 times smaller than the last one. This is 1 divided by 10. 0.1 divided by 10 is 0.01. 0.01 divided by 10. So in each case, we're dividing the previous number by 10, and we're going down 1 log unit. So even though we're dividing by a full 10, we're only getting a 1 log unit change. And again, what this helps us do is simply express phenomena that occur on really big scales and squish them down to relatively small scales. For instance, in chemistry, we have this definition. You might remember this from chemistry. pH is equal to minus the log of the H plus concentration. If you don't know this one, fine, we'll get to it in second semester. But we can have a H plus concentration of 10 to the minus 1, or we can have an H plus concentration of 10 to the minus 14. This would be 0.1. This would be 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So notice how big a difference that is in these numbers. There's a scad of numbers in between these two numbers, right? On a pH scale, though, when we apply this definition minus the log of that number, we take the exponent comes down. So in this case, we'd get minus 1 times the log of 10. Well, minus 1 is just 1. So this becomes a plus 1, and the log of 10 is plus 1. So the pH here would equal 1. And the pH here, minus 14 comes out, so we get minus 14. We still have to multiply by the log of 10, but the log of 10 again is 1. We get a plus 14 here, so we have 14 times 1, so we get a pH of 14. So our pH scale typically runs between 1 and 14. We say that, a pH of 1, a pH of 2, you might know that a pH of 7 is considered neutral, right? So pH equal to 7 is equal to neutral. We could say, well, what H plus concentration does that correspond to? Mathematically, we would need to do the anti-log. Right? So if this were the case here, in this case, the 14 came down and there was a negative outside. In this case, we'd have to swing the negative over to the other side, and we get negative 7 is equal to the log of H plus. But that would mean that the H plus concentration is equal to the log of 10 raised to the minus 7. To cancel the log, we have to take both sides, take 10 and raise it to both sides. You might have seen that operation. So the H plus concentration, the H plus concentration here is 10 to the minus 7, not the log of 10 to the minus 7. H plus is just 10 to the minus 7, or 0.00000001. Now, what's easier to say? pH is equal to 7, or H plus is equal to 0.000001. If you're in a class and you need to write this down in your notes, or you're at a conference, or you're at a business meeting, and somebody says, what's the pH of that solution? And somebody says the pH is 7. So the whole room is thinking in terms of pH, and the whole room knows that it is a logarithmic scale. The whole room knows that definition. It's a lot easier for people to understand the sentence pH is equal to 7 than H plus concentration is equal to 0.000001. Because again, you get into that. How many zeros was that? What did that say? Was that 6 zeros and followed by a 1, or was it 7 zeros followed by a 1? And you'd have to raise your hand and ask and interrupt a conversation or write it down incorrectly. So again, the logarithmic scale just helps us communicate big and small numbers by simplifying them to whole numbers that we're more used to dealing with. There are several other systems that deal with logarithmic scales. So I noted in chemistry, pH is one. When I was looking this up to make this video, noise, volume, the decibel system is also a logarithmic system. So 10 decibels and 20 decibels and 30 decibels are in fact 10 orders of magnitude different in volume. It's not a linear, this makes it look linear when we say it's a decibel and 20 decibels versus 30 decibels. You might think 10 to 20 is just twice as loud. It isn't. It's 10 times as loud because the decibel is defined as a logarithmic unit, just like pH is defined as a logarithmic unit. So the pH of 2 and a pH of 3 and a pH of 4, this is not twice that. It is a factor of 10 followed by another factor of 10. This is 100 times smaller. pH 4 is 100 times smaller in H plus concentration than pH 2. And if we went to pH 5, it would be 1,000 times smaller. And if we went to pH 6, it would be 10,000 times smaller. So each step is tenfold. Right? So if we go up to 40 decibels, we'd be 1,000. That would be a 10. So it'd be 10 times 10 times 10. We'd be 1,000 times louder than 10 decibels. Not just 4 times louder, 1,000 times louder. Right? So when you go to concerts and you hear about decibel levels and things, or football stadiums, that's being measured on a logarithmic scale, as is, in fact, the Richter scale of earthquakes. So a earthquake of magnitude 4 and an earthquake of magnitude 5 are not just one linear step away. I believe it might even be a factor of 100 between those two. I don't recall if it's just a factor of 10 or if it's actually a factor of 100 in the Richter scale. But you can imagine, if something is liberating 10 times as much energy, that's important for us to recognize. So the problem with the logarithmic scales is it squishes the numbers. 6 doesn't seem that different than 5, but we have to remind ourselves that it's actually an order of magnitude, 10 times greater. Right? The last thing that I wanted to do with this is simply a couple rules here. We could take something like the log of 3 times 4, and that would clearly be the log of 12. And if we take the logarithm of 12, we get 1.079. Okay. That doesn't seem too bad, but what I want to show you is that this is in fact the log of 3 plus the log of 4. So if we independently evaluate the log of 3, we get 0.4771 plus the log of 4, you get 0.6020. Now, if you add those two things together, you get 1.079. So now we have a new mathematical operation that we can introduce with logs, one that comes in very handy when we're solving problems. That is, if we have any two numbers multiplied by each other, log of x times y is also equal to the log of x plus the log of y. So notice the parentheses here are important. This would say take the log of whatever the product of x times y is. Notice the first thing I did is I took 12. This is not saying the log of 3. This is not equal to the log of 3 times the log of 4. We're not carrying that multiplication sign through. That's not correct. First thing we'd have to do is multiply, then we take the logarithm. Or we could take the log of 3, add it to the log of 4, and we get the same answer. Similarly, for division, if you were to say log of 5 over 7. So if we do 5 divided by 7, this would be the log of 0.714. Take the log of that number, you get negative 0.146. Or we could say the log of 5 minus the log of 7. Take the log of 5, you get 0.6989 minus 7 log 0.8451. And if you take 0.6989 minus 0.8451, you in fact get back 0.146. So we have another mathematical function here that's very useful. The log of x over y is equal to the log of x minus the log of y. So those are two things to remember. Log of x times y can be broken up into log x plus log y. Log of x over y is equal to log x minus the log of y. Lastly, we talk about log 10, and we also talk about ln 10, the natural logarithm. We often find in science that a lot of processes like radioactive decay or the rates of semichemical reactions depend on a logarithmic scale. And that nature just seems to operate logarithmically sometimes. So if we take the log of 10, we saw before that we get 1. Go ahead and in your calculator, type in 10, and then if you have an LN button, do that. And what you should get is 2.30, call it 3. Okay, you have to round up. Okay. So notice here, I'm going to substitute in a variable x. So we have log of x and log of, natural log. We have the base 10 log of x and the natural log of x. Now there's a relationship here. We saw that this was 1 and that was 2.303. If we were to take this side and multiply by 2.303, we end up getting what we get with the natural log. So there's another identity that if we say 2.303 times the base 10 log of x, we get the natural log of x. So let's go ahead and prove that to ourselves. Pick a number. You can pick a different number than I'm picking. I'm going to pick my favorite number, which is 11. So if I take the base 10 log of 11, I get 1.041. So I take 2.303 times that. And if I just do that calculation, I get 2.398. And now what I'm saying is that should equal the base 10 log of 11. So if I just do 11 and take the natural log of it, I do in fact get 2.398 when I round. And that will work with any number. I chose 11. You could choose 7,413,328. Take the natural log of that number, multiply by 2.303. I'm sorry, take the base 10 log of that number, multiply by 2.303, and you will get the natural log. The reason for using base 10 logs is, as I showed before, it's a very easy scale because it's based on the exponents that we saw before, and that if we take the log of those, we just get the exponents. So it was easy to estimate what the answers of those would be pre-calculator days. It is not intuitive that the base E log, or the natural log of 10 is 2.303. But if we do remember that conversion, we can work in base 10 logs and then multiply our final answer by 2.303 if we want the natural log. So those are a few operations with logarithms that we encounter in general chemistry that you may have seen before, but are certainly worth refreshing your memory about. And I will likely post a very brief problem set related to those operations shortly. Thanks, and I hope this was useful.